Hi, class. Today we are going to introduce, this is kind of exciting, the last 5 rules we will be using in this course. The rest of the assignments after this are on general topics and not proofs. So um, these 5 rules have to do with quantification. Um, so put another way, remember everything we said in the previous chapter still goes. We have all the rules of implication. We have all the rules of replacement. We also have indirect proof and conditional proof. Don't forget that. And so all of that is old hat. And as Ulrich pointed out right at the beginning of 7.1, sometimes that's all you need, that even if a proof has quantifiers in it, nothing about that actually entails that you're going to need any of the new rules, because some of them can still be done using the rules we already had. So don't forget what we've learned before. Speaking of things we learned before, don't forget that when we were learning translation, we learned how to deal with negations. That if it's not true that there exists a mu such that mu, this is saying something does not exist, which is the same as saying is logically equivalent to for all mu, it is not the case that whatever. So, sorry, these look a little messy. I'm not that good at drawing Greek letters. But also the necessity of the form here. So remember, mu is used just to kind of represent anything. It's a pseudonym. And so just whatever you fill in the quantifier here just has to be the negation of anything within an existential quantifier is logically equivalent to universally negated within. So this is the rule that moves a negation, that gets rid of a negation or adds a negation to the existential quantifier. And that rule, by the way, is called quantifier negation, QN. But notice, this is effectively a rule of replacement, right? This is logical equivalence. And so pay attention to that, because our other rules aren't going to be like that. So this one, unlike the other quantifier rules, you could do to any part of a well-formed formula, etc. And then going the other way, if we want to add or get rid of a negation in front of a universal quantifier for all mu, blah, 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 this is saying not all, which is equivalent to saying some are not. So, a little closer there, I guess. So that's formalized what we already knew as quantifier negation. Its use is relatively self-explanatory. If you want to add or take away a negation from a quantified statement, that is the whole show. So, after that, the only other things we need to do is learn how to put on and take off quantifiers, how to add or take away an existential quantifier, how to add or take away a universal quantifier. And the rules, all of what's common to all 4 of these rules is just this isn't so much an inference as learning when you're allowed to do it. When can you infer a quantifier? So, for instance, the easiest one, I'm not going to go in the same order as the text, the easiest one is simply existential generalization, or EG, that is, we're doing this to add an existential quantifier. And this is the only rule that lets you add an existential quantifier. And here's what the rule says. Well, there's something or other with a pseudonym or a constant in it. From that, you may basically change it to that, where all instances of alpha become instances of mu, and mu is not already occurring somewhere else in the original. So Justus and Ulrich go into quite a bit of detail, and rightfully so, about why these rules are what they are. But just think about it. Well, if it's true that Socrates is a philosopher, it's true that someone is a philosopher. And so if you use cases like that, this is one of the reasons we emphasize translation so much. It'll let you kind of realize, well, yeah, I could just put an existential quantifier there and replace Socrates with somebody. The pseudo variables u and v. Somebody or other I always like to think of, or the whatever. Something like that is how I like to think of it. So that's the existential generalization. That's the easiest one. It's the fewest restrictions. So that's if I want to add an existential generalization. However, suppose instead I want to take one away. That's called existential instantiation. And think about what you're doing. You're going from, well, there's some mu such that blah, 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 mu, to replacing that mu with a beta. And you might think in terms of, well, when would I be able to do that? And again, it helps to think of some cases. Well, there exists somebody who's the tallest person in the room. Well, you can't therefore say that Jack is the tallest person in the room. Instead, there has to be a limitation on what you're allowed to do. And in this case, part of that is because beta is a pseudonym. It has to then be a pseudonym, not a constant. So you can't just assert that Jack is the tallest person in the room. Instead, you replace it with a pseudonym. When are you allowed to do that? When beta doesn't occur on an earlier line, and all the resultant changes are the same. Now, you notice that in some senses you might say, well, how does that help? Because, well, if I just replace mu with a pseudo constant, if I just say, you're basically saying, going from there exists someone who's the tallest person in the room to someone is the tallest person in the room. That's effectively what a pseudonym is. Why does that help? Because then basically what you're really doing is you're using these two in conjunction, right? I can take the quantifier off, do my other inferences, and put it back on at the end. That's the general idea behind why you might use these. And something similar goes for some of the other quantifier rules as well. But before that, just to show you, I'm just going to do some of the really simple ones on page 220. So, for instance, if you look at number 2, it says there exists an X, and I encourage you to keep reading these because it really kind of helps you lock in what you are allowed to do and what you're not, such that fx and gx. So your typical I statement. From that, it follows that there exists a Y such that Fy. Well, this is a good example because if you realize what the words mean, it clearly follows. Well, if there's something that's both, then something must be at least one. Notice this doesn't say only one. And so that's one that we might have to do here. And again, what are the problems? In this sense, what's the difference? The difference is that the original has an F and a G, so we have to get rid of that. But then it also has a different letter, and so this is very clearly an example where we're going to have to strip off some quantifiers and put on some more quantifiers. So I call this premise 1. Sorry, I didn't set it up like I usually do. Okay, so what do I need to do? Well, let's get rid of this. So 2, I'm going to strip off my existential quantifier using line 1, existential instantiation. And when I do that, I'm going to use a pseudo variable v. Notice capital and lowercase are very important. And so then, before I finish that, I'm going to double check to make sure I use the existential instantiation right. Does V not occur on any? Does V occur on any previous line? Nope. So it's fine there. Does it result from line 1 only changing x to v with making no other changes? Yes. Then that is a perfectly allowable rule of existential instantiation. Now I can do some of my older inferences. Well, I need to get rid of the G, which is to say I need to break up a conjunction. I can do that no problem with simplification. As usual, there is no new anything there, because remember, we know that simp is good for anything of that form, and that anything includes sentential logic and predicate logic. So that is good to go. And now I just seem to need to slap a quantifier back onto premise 3. So can I do that? Well, what adds a quantifier? It's it's existential generalization. So can I do an existential generalization to get what I need? What do I need? There exists a y such that Fy. Well, let's see. So what are my requirements for existential generalization? First of all is y something that doesn't occur in 3? Yes. Second of all, does line 4 result from line 3, where the only changes I make are replacing v's with y's? Yes, which means I've done it, and I've done that proof. That's a very clear example of a couple of things, why you might need it, but also the importance of pseudo variables. So there exists someone who is the tallest person in the room and is bald, therefore there's somebody who's the tallest person in the room. So roughly speaking, that's how we do it. Let's do one more of the simple ones from page 220. I will do, let's do number 3. So number 3 states, Premise. There exists an x and there exists a y such that x bears a relation to y. From this, show me that there exists a y and there exists an x such that x bears the relation to y. So, first of all, this is not an utterly trivial proof in certain senses. It's like when you have to do com before you simp. You know that one follows from the other. Having said that, you are working within a system that has a finite number of rules. You don't want to memorize 600 rules, and so sometimes you have to kind of demonstrate that the easy inferences are good inferences. So, how are we going to do this? Here is an interesting one simply because we're going to have to strip off 2 existential quantifiers and put back on 2 existential quantifiers. So, not that hard. We're doing something to the similar to the above. So, premise. You always have to work from the outside, by the way. So you have to take you have to work from the outside in, so you have to take the first one off. So I'm going to take the x off, replace x with a pseudo variable such as v, and leave the y there, and that is line 1, existential instantiation. I'm not going to go through the checks because it's the exact same as this one. But now I have to do it again. And so we're going to take the y off and let's say replace it with u. And then that's line 2, existential instantiation. So no problem doing that. And now I have to put them back on, and this is a good proof to remind you, putting them back on, you kind of end up doing the opposite, working from the inside out as you put them back on. Sorry, there shouldn't be any parentheses here, my bad. So I'm going to replace the v with an x, and that is line 3, existential instantiation. And notice, so again, that's fine because x was not occurring in line 3, and I didn't make any other changes. And then just have to do it again. There exists a y, and there exists an x, such that r x y. Oops, EG, LTG. So these are just very common ways to how we use existential generalization and existential instantiation. So obviously you're going to have to play with the proofs yourself tonight, but I just wanted to give you a very, very quick example of those 2 rules before we cover the last 2 rules, which are a little trickier. Actually, that's not true. One's simple and one's tricky. And you might realize that because of what they say. Universal instantiation is a rule that takes a universal quantifier off. And that, if you think about it, think about what it means, and again, the way you're not going to get confused with these is remember what they mean. This means for all mu, whatever mu you could think of to put in there, which means there's not much of a restriction Well, if it's true of if it's true of everything, then trivially it's true of alpha. And so notice, among other things, like existential generalization, you can actually do this to a constant. If it's true of everything, it's true of Jen. um, just like with existential generalization, if it's true of Jen, it's true of someone. So remember, your universal instantiation and your existential generalizations, those are the easy inferences. Those are the ones you're allowed to do with a pseudonym or a constant. So, and those are the only two. Notice that the other two, existential instantiation and universal generalization that we're about to get to, you can't do a constant because it doesn't follow. So again, translation is important. That's why we spent last week on it. So with existential generalization, if it's true of Jen, it's true of somebody. Your universal instantiation, if it's true of everybody, it's true of Jen. You're allowed to do those. And that's the easy rule. By contrast, is universal generalization. Now remember, this is going from some beta to, for all mu, and that should be much more limited if it's because if it's true of this form, it's true of everything of this form. That's not a good inference. And there's two ways in which we make sure it is a good inference. First of all, as previously mentioned, you can't do it to constants. You can only do it to pseudonames. So like the two practice proofs we just did, universal generalization pretty much only happens to pseudonames. That is basically when we already have a variable and we're just putting a quantifier on it. So for instance, if we've already universally or existentially instantiated and we're just putting something back on it, so that by itself is a huge restriction. But then there's 4 other restrictions, and that's actually really important, by the way, because there's another logic text, Hurley, A Concise Introduction to Logic, who, like, the first 9 editions, he actually had universal generalization invalid. I don't mean this to dig at Hurley. Hurley's very, very bright, very decent text overall. But I just emphasize it to say there's a reason we put all these qualifications on universal generalization. You're trying to do something very hard, and so as a result, you have to be really careful about it. On the plus side, so this exam, like the others, will be open note. So, but it really helps to kind of realize what you're doing and kind of in English, so you know what you're not allowed to do. So you're not allowed to use a mu that occurs in a conditional proof that hasn't been discharged. You're not allowed to use, you're not allowed to go from here to here if beta hasn't been in a conditional proof that hasn't been discharged. Beta also can't occur by existential instantiation. So if you got beta from EI, you're not allowed to do it either. And again, Gustafson, Ulrich really kind of worked through why these requirements exist, but existential instantiation is a sum. So line 2 basically says you can't go from sum to all. The third requirement is that mu isn't already occurring in beta. And then lastly, the usual replacement of each occurrence. And so 2 of them we're kind of used to. The other 2 can't be in an undischarged conditional proof, can't be from EI. And again, the big one is it's a pseudonym. It cannot be a constant. So those are the rules. We're going to spend 2 weeks doing 7.1, but I will just do one of the little baby proofs, probably one that's in the back of the book, just to walk you through it, and then doing one out of the back of the book just so you still have some to practice. So I guess I'll do number 6 on 229. All right, so number 6 says, premise for all x, bracket parentheses, if it is the case that x has property B or x has property C, then x has property D. So again, I try to read these kind of out loud, so to speak. It helps to make sure I wrote them down correctly, but it also kind of helps to, when you realize what they say, kind of helps with see how the inferences go sometimes. Premise 2, there exists a y such that y does not have property C, or y does not have property B. Lastly, there exists a z such that it is the case that neither z has property E nor z does not have property C. From all of that, it follows that there must be a D. There exists an X such that it has property D. And roughly speaking, you can kind of see how that follows from the premises if you, again, read them out loud. Well, if something exists that doesn't have these, but something exists that has those, well, something must exist that has that. But notice what an easy proof this would be, roughly speaking, if we didn't have all those pesky quantifiers on there. And so the main thing to do is to simply strip those quantifiers away in a way that we are allowed to. So we can start in a couple of places. In general, I like to start with the quantifiers that are easy to take off, and remember those are existential generalization and universal instantiation. Those are the easies. So the other option to do it is if you start with the hards, just make sure you can strip them all off. Maybe I should say that. So I usually start with the easy ones just because I'm pretty comfortable knowing what's allowed to strip off how. If you are not comfortable with that yet, then it does make perfect sense to strip them off and kind of starting the harder ones first. But it doesn't matter much. So roughly speaking, I need to get to here. I look at, I kind of ignore the quantifiers. I look at the conclusion. Does it occur anywhere in the premises? Right there. What do I need? I need Bx or Cx with the modus ponens, roughly speaking. I say roughly speaking because I don't tend to write the quantifiers on the side. I assume that if I get it all right, it'll work out okay. So I need to universally instantiate this in a way that's going to match a bx or a cx. So notice I have a b here and a c here. Let's see what we can do. I'm going to go ahead then, do the beginner method. If you have trouble seeing what can come off and how, we'll go ahead and do the harder ones first. Let's start with stripping a quantifier off premise 2. How do we do that? That is an existential instantiation. Well, there exists a y. Can I go from there exists a y to not the pseudo variable, that's a v, or not b pseudo variable v. This is because we're using a pseudo variable, there's no problem. This goes from saying there exists a y to something or other has it. Again, I like to read my pseudo variables as something or other. No problem. That's a straightforward existential instantiation. We've done a couple of those. Then what? Well, now we have to strip 3. And here's the tricky part. Because remember the rules of existential instantiation? We need to go to a beta that does not occur in an earlier line. And so that's the one that if you haven't had enough practice on it, you might get in some serious trouble. So it might be tempting to just go from line 3, existential instantiation, to something with V, because then they match up and all is good and everything's wonderful. But you're not allowed to do that. The first requirement in existential instantiation, our beta cannot occur in an earlier line. And so instead of instantiating to V, I'm going to instantiate in a U. So not the case that some U or other has property E, or not U or other. So that's a pretty simple one. But now I have a negation outside of parentheses. Obviously, De Morgan's is the only thing we have for that. And again, emphasis just doesn't change. Line 5 De Morgan's, and then got to change that to an and. Okay. And double negation. So now what are we going to do? Well, what we're actually going to try to do then, we need this C. Notice nothing about the U's up here. So I'm going to com. Just realized my U's look a lot like my Muse. Maybe I should just use V prime in the future. Not E, U, 7 com, and now that gets me a C with a U all by itself with simp. Okay. So now, what are we trying to do? Well, I'm trying to get to this up here. And so now I could do that with line 9. So line 10, I could certainly go CU or BU by using line 9 addition. And then BU or CU using line 10 com. And so now I know what I need to instantiate with my universal instantiation. Let's go ahead and go. If it's true of everything, it must be true of pseudo-variables such as u. That's line 1, universal instantiation. And notice, if it's true of everything, it's true of whatever you feel like, roughly speaking. There are very, very few restrictions on universal instantiation. The only restriction is you make sure that you do it right, that you don't change anything by accident. Nope, sure looks like it. Which means now I can do a simple modus ponens, lines 12 and 11 to get du. And now, if it's true of a pseudo variable, it must be true that there exists one such one using existential generalization. And notice, again, I don't spend a ton of time double checking on EG because it's very, very unrestricted. If it's true of a pseudo variable, it's true of something or other. The only restriction besides no changes is it can't already be occurring in you. That's to avoid things like, by the way, well, there's something that's not bx and not cy. You can't switch this to an x. That's what that first requirement means. Whoops, off camera. But yeah, if you have a not bx and not cy, that's saying it's neither of those things. You can't just switch it to saying it's not y. So that's what that first requirement means. Otherwise, it's pretty darn wide open. So that's how you use these overall. You are going to confuse yourself if you don't understand what they mean. That's why 7.1 spent so much time talking about that. Well, where do these restrictions come from and why do they exist? Will help you use them right. You don't want to just be sitting there scratching your head and saying, can I do that? Every time you do a step. If I know generally what these say, that this is true of everything, so it must be true of mu. This is true of mu, so it must be true of something or other. As soon as I realize that, I can go through these checks pretty darn quickly. And so one thing you really want to pay attention to this week is the restrictions. We're going to work on that in the exercises too. But otherwise, read the chapter carefully, and that's my advice. Keep translating. Keep really fathoming what these things are saying. Even use some substitution instances if you want. And we will see you next time. Next video is just going to be practice, practice, practice.